Okay, great. So welcome back. So we're going to kick off today. It's mostly a sort of a tutorial and hands-on day, but we do have one lecture from Mike. And now that you're all sufficiently expert in DIA, how things are working, Mike is going to tell us a little bit about what the most kind of current developments are and maybe a little bit about how things are going to keep going. Thanks, Mike.
Yeah, so I've got a lot of material kind of packed into this next hour, so it's going to be a little bit of a whirlwind, I think. So just kind of bear with me a bit, and the slides will definitely be made available for people who want to look over it afterwards. And I'm also happy to talk with people after the fact as well. So I gave this a title, Recent Developments and Future Directions, but I also looked at some of the things were done in 2013. So it's not too recent, but at the same time, they are very much kind of advanced, more advanced topics around DIA. So I just want to remind people that DIA is about this sort of balance and sacrifice. We balance three major things: the mass range, the isolation window, and the duty cycle. So and I think this has been beaten to death during the course. But this is an important component, and it's something to consider when you're definitely thinking about building a DIA method for your use. So our lab started thinking about a decade ago, how do we have a single method that could sample comprehensively, minimally from 500 to 900, but ideally from 400 to 1,000. Has narrow precursor windows of less than 4 mass to charge. The main reason for 4 mass to charge is that there's this critical unit in peptides. It's a carbon and 2 hydrogens, so CH2. And that's 14, and that's the most common unit that you get from a sequence variant. Availing to a leucine, a serine to threonine, to aspartic acid to glutamic acid are all 14. Most modifications like oxidation, et cetera, or acetylation or trimethylation are all larger in mass than that difference. So we want to have our precursor windows of less than 4 mass to charge. So that way, basically, a 14, a doubly charged thing would be 7. A triply charged would be 4 and a bit, right? So it can cover the breadth of this range within about 2-second cycle time and fills an ion trap. In our case, we're thinking about Orbitraps or actually even linear ion traps. I won't get into that today, though. So this is what got us thinking about this about a decade ago. And so one thing is that in mass spectrometry, we have this crazy way in which we tend to think about things in series, but no other field really thinks about this. So I'm sure people have kind of seen these sorts of like riddles before where, okay, you've got a bunch of buckets and one of the buckets differs in the amount of volume. What's the minimum amount of measurements you can make in order to figure out the volume of that bucket? This is basically what we do in mass spectrometry, right? So you want to know what is the intensity of any fragment ion between these 20 or 30 precursor mass to charge windows. So the way we currently do this is we go and say, all right, we just weigh each bucket, right? And we then take the second one. And this works. We basically get through this, but it's the most slow, most inefficient way of doing this. And I'll point out that no other field does this. But yet at the same time in the mass spectrometry field, we've done this repeatedly over and over again, whether sampling DDA precursors, whether or not we measure parallel reaction monitoring species, et cetera. Data independent acquisition by nature is something that measures things in parallel and multiplexes the MSMS. And so what we do is we take an extra dimension to that. Okay, so you can imagine a case where you go and measure multiple buckets at once, measure the weight of that and say, okay, then you can take another set of buckets and then realize, okay, this is definitely the one that's got to have this extra double amount of water in it. So then you know that these ones are not. And then you can then narrow down on just figuring out which of these buckets tend to have the extra amount of water in it. Ultimately, you can figure this out in about 3 or 4 measurements, and largely this comes down to what people call as the data sparsity. And so what this means is what fraction of your data has the extra amount of water in it. But this is a common method. If you go in for an MRI, MRI imaging analyses are all done using a compressed sensing approach. There's also these methods called single pixel optical spectroscopy, and those are also done by using compressed sensing strategies. So this is a fairly new area in computer science, and it's being used in lots of different clever ways. Okay, so when we first saw in about 2010, this I remember seeing a talk with Alexander Makarov and chatted with him shortly after. When I saw this configuration of an instrument, I thought, geez, this is actually a really clever instrument design, right? So they were using the instrument as filling with the quad, fragmenting, collecting the ions in the C-trap, and measuring them in the Orbitrap. So what we began to think about instantly was, could we use the quad filter, select a mass, fragment, store the fragments, select another mass, fragment, store the fragments, et cetera, and then measure a mixed set of spectrum from multiple independent portions of the mass range. So just like Ludovic pointed out, you can, on some cases, get to the point where the C-trap fill is only a small portion of the total acquisition time. So if you look at time, what's being done in parallel, there's a parallel from the previous scan is you're filling the C-trap, and then you're moving those ions into the Orbitrap for mass analysis. Well, in parallel, you're filling the C-trap again for the next scan. So what we wanted to do was basically multiplex this. And we didn't realize at the time that there was some limitations as far as the ion transmission, et cetera. But this became our idea from the start, as to be able to do this. So if we had 100 4 master charge wide windows, that would span this 500 by 900. So what we'd want to do then is in scan 1, randomly select 5 of these 100 windows. Select them individually, isolate them, fragment them, and store them, and then do the next ones. We do the fills in series, but we collect a spectrum that's a mixed spectrum of these 5 separate 4 master charge wide windows. Scan 2, we do the same thing again, but we do of the remaining 95. And when you get down to scan 20, there's only 5 left, and we do that again. And then scan 21, we fill this list again, and then we randomly select 5 scans. So what's kind of cool here is that now, if you're looking at the fragment ions in scan 20 and scan 21, there are the shared isolation window. So the fragment ions that are shared between scan 20 and 21 probably belong to the same precursor window. Those that are different probably belong to any one of the remaining 9 different fragmentation, or 8 different fragment isolation windows. And we published a paper on this in 2013 in Nature Methods. And the basic idea is now you have a mixed MSM spectrum where each product ion could be the linear combination of multiple different components from the different isolation windows. And you could draw this as just a simple sum. For scan number 100, you have it the sum of isolation window 1, 7, 28, 81, and 84. And you can't solve this equation, obviously, because you don't have enough information. But if you actually go from enough scans forward and enough scans back, you then have to the point where you can get 100 knowns and 100 unknowns, and you can use a regression strategy to actually solve for the intensity of all the individual components. Now, this is a lot of kind of math, and it's kind of like kind of hand waving, but I'll just kind of show you that this actually works really well. And this takes about 15 seconds, so it's about half of a chromatographic peak width of information. I'll also point out too that this actually takes a Savitsky-Goulet strategy for weighting these different input intensities prior to calculating this value, so it doesn't actually distort the chromatographic peaks much at all. So here's what the data looks like. So if I had 10 mass to charge doing DIA, actually this is the 20 mass to charge wide isolation window, where I'm measuring 20 mass to charge worth of information in each individual scan. And I'm doing DIA, so this is what the DIA data looks like. As you can see, there's lots of different peaks that show up for my individual target peptide of interest. And if I extract the data and blow up into the retention time region, you'll notice I can easily detect this peptide, and I can probably easily quantify this peptide too. But it would actually be fairly hard for algorithms to actually pick this signal versus something else that's there. But if you demultiplex it down to 4 master charge worth of data, you actually get the specificity as if you had a 4 master charge isolation window. This is what the data looks like. And you'll notice that this would be much more preferred to use this for quantitation and detection than it would be to use this one. You're basically gaining 5 times an improvement in speed without actually going any faster. Okay, so here's just showing this another way. So this is actually measuring 10 master charge wide DIA, which Alexei pointed out yesterday is pretty ideal. It offers a lot of advantages. It's kind of this good balance between breadth and also some selectivity. But if you were to pull out this peptide, there'd still be a lot of product ions showing up there. It would be hard to actually point this retention time as being your individual target. If you collect 20 master charge in any one scan and demultiplex it down to 4, this is what the data looks like. This is much more selective, obviously, than this. And if you blow up the chromatograms, it looks even better. So yes, you can still get good quantitation off of this. If you have a really good, strong retention time filter, you could still pick this peak. But in general, this data still is much preferred over this signal. Here's just another example. 10 master charge with the data in each scan versus 20 master charge with the data in each scan, demultiplexed down to 4. And so again, the data looks really nice. And yes, you can still quantify off of this peak, but this is definitely preferred over this. Okay. So what's the problem then? So when we did these experiments, we initially did these things on a QE Classic, then we started to do them on a QEHF. Both the QE Classic and the QHF and the QE Plus have the same problem, and that is that they don't quite have bright enough of a source. So if you're collecting a transient for about 60 milliseconds, it basically means you have about 60 milliseconds in parallel to potentially fill the Orbitrap. If you're trying to fill this with 5 separate isolation windows, that means you only have 12 milliseconds basically for each one of those individual fills. So you're not really providing it enough time in order to gain enough ions. So if you look at through each of the individual scans and you look at the number of ions that were in each spectrum, most of them, this is our AGC target, which was 10 to the 6th. We noticed that most of the spectra tend to be significantly underfilling from what our target goal was. This changed a little bit when we went to the Lumos. In this case, we noticed that in an overwhelming number of the cases, especially when most of the peptides were coming out, the chromatography is very different between the two here, that we were getting a much higher percentage of our scans were actually filling the Orbitrap. And the reason for this, of course, is that the Fusion Lumas actually uses a true ion funnel, electrodynamic ion funnel. And we knew that this would actually be important. And we had been encouraging Thermo to kind of switch from using a stacked ring ion guide situation to using a true ion funnel like is on the Fusion Lumos. I'll point out we have not tried this on the QEHFX, but there's no reason why you wouldn't expect that the same advantage to be available on the QHFX. So I'll point out that that this now brings into question is whether or not you should even be using wide isolation windows at all, because now we're filling the Orbitrap in every single scan. Even though we're collecting 20 master charge worth of data in every scan, we can demultiplex it down to 4. Okay, so this is still we haven't published this yet. We're still kind of working through a manuscript on it, but this was definitely very appealing to us. This is just showing this another way. This is what percentage of the spectra hit the maximum inject time, and you look at the QEHF. Basically, every single scan hits the maximum inject time. When on the Fusion Lumos, when you're looking at where a majority of the peptides are coming out, when the majority of the peptides are coming out, we're actually at a maximum inject time much lower than the maximum inject time. It also gets very confusing between San Jose, which is where the Lumos is made, and Bremen. Bremen considers the maximum inject time the sum of the 4 or 5 mass charge wide windows, which is 60 milliseconds. And in San Jose, they consider the maximum inject time per isolation window, which is the 15 milliseconds. So it's a little confusing, but the point here is that we do get to the point where peptides are coming out and are most intense, we do fill the Orbitrap, and in the QEHF, the QE Plus, or the QE Classic, we don't. So in our lab, we still make heavy use of QEHFs. We also know that a lot of people do a lot of work with QTOFs. So we wanted to find another way to try to improve the selectivity. And actually, this was The second graduate student ever in our lab, a guy named Mike Hoopman. This was actually his rotation project back in 2004, believe it or not. And we were doing this on an LTQ at the time. And the idea here is that if you have these wide isolation windows, and you have two different molecular species in an isolation window, when you isolate them and draw chromatograms, if they share product ions, you would see some sort of interference, where the target one is the solid line and the interference is the dashed line. So a simple idea that we had going back to 2004 was, could we stagger these isolation windows in alternating scan cycles? Again, this is very similar to like a Hadamard transform type strategy. And in this case, if you were to extract the data for this precursor mass for the target peptide, which is the solid line across time, you'd pull it from this blue scan, this red scan, this blue scan, etc. So the interference will be present in the blue scans, but not present in the red scans. And this is what you see. You'll see this sort of sawtooth pattern right here. So when you look at an individual chromatogram for 20 master charge DIA data, and you look across extracting the chromatograms, you're not quite sure which retention time peak to pick for this target peptide. If you overlap the windows, you can see right away that some of these peptides have the sawtooth pattern and some do not. This means that they're in the other half of the isolation window now. So this means that they're at least 10 master charge away in the precursor. And you can demultiplex that using that same non-negative least squares equation. It's really easy to apply. And to be honest, it actually gives you almost exactly the same data as if you actually collect the data with 10 master charge. So here's the data collected with 10 master charge worth of data. It's completely indistinguishable from the 20 master charge with the data with overlap plus demultiplexing. There is a little bit of a catch, and that is that you need to make sure that your quad isolation is fairly uniform. Originally with the QE Classic, the quad isolation was not very uniform. Since then, Thermo has put in segmented quadrupoles on all of their instruments, largely because of data from this experiment. Because basically what you need is the transmission on the left-hand side of the isolation window to be very similar to that on the right-hand side. There is a little bit of edge effects, but they're actually fairly minimal, given the way we put our edges of our DIA boundaries not at integers. We actually put them at offsets, in what's called forbidden zones. Alexi talked a little bit about that yesterday too. And so we actually have the quad isolation on these on either the QE plus HF, the Lumos, or the HFX is actually very uniform like this. The Fusion and the QE plus and the QE Classic is not nearly as uniform. So just to kind of give you a sense of quantitation, so if we take a strategy where we say, give us the top 3 product ions from the spectrum, or top 5 product ions from the spectrum, or top 7. I'll explain this a little bit later. In our lab, we actually don't use this strategy, but this is the way a strategy people often use with Open SWATH or Spectronaut. If you say, give me the top 10 or top 5 from a given spectrum, and you compared it from using the MS1 data. This is 30 bovine peptides spiked into a complex yeast background. If you use the MS1 data versus the 20 master charge data which is overlapping versus the 10 master charge data from non-overlapping versus the 20 master charge that's non-overlapping, which is in this green, you'll notice that the 20 master charge overlapping is basically the same lower limit of quantitation, which is substantially better than the 20 master charge non-overlapping. And also, you'll notice too that even the 20 master charge non-overlapping is now giving about a similar lower limit of quantitation than that of the 20 master charge in some cases. So this is, again, showing that the lower limit of quantitation is better when you do MS-MS with narrow windows, and we gain back the same effect of having narrower windows when we use overlapping windows than if we use just the 10 master charge. There was a problem, and that was originally when we implemented this in Skyline. There was the way Jared Egerton implemented it. It sort of did it on the per transition level. And so the number of transition, and in our lab, this ended up being fine because we tended to do fairly, initially we tended to do fairly defined experiments of these 100 proteins or so, but we started to see people wanting to demultiplex millions of transitions, and you can see here that it just caused this explosion in the processing time to import the data when it went into Skyline. So there was a fairly big effort to try to think about a way that would go through the file in one read and using and be able to apply the demultiplexing strategy to every single spectrum that was in there. So you basically could output an MZML file that was completely demultiplexed. And so regardless of the number of transitions that are imported, the processing time to generate the demultiplex file was constant. And I'll point out that the ProteWizard now has this ability to demultiplex it directly, so there's no reason not to use this. So if you overlap your isolation windows using an isolation scheme derived from Skyline, there's no reason that you shouldn't demultiplex the data, and you can tell it to demultiplex and overlap it. You generate an MZML file, and then that MZML file can be used within Skyline. You're basically gaining an instrument that's twice as fast for free. So I pointed out yesterday that this is the most common strategy that people use to process data. They basically take a spectrum library, a wide window DIA file, compute some scores, and then have some sort of machine learning classifier. So we started, it was I think about 6 or 7 years ago, with a couple of graduate students in the lab, started to think about could we come up with some new tools for data independent acquisition. So one was we wanted basically a query engine for DIA data. So if you had a new interesting peptide that you were interested in, one of the values of DIA is that you can go back to the data and reanalyze it for new things as new hypotheses come up. Someone reports a new alternative splice form. Can you find the peptide spanning that alternative splice form? That peptide may not be present in any spectrum library, so you wanted the ability to just take the peptide and query the data against it, or it against the data. So we wanted one that didn't require spectrum libraries, just could take peptide sequences. We needed and expect as good or better peptide detections and DDA, at least if you have results there. This actually wasn't something that our lab was felt that important by. We really wanted the best quantitation, but we found that all the papers we submitted for review expected us to have big lists. So we began to feel like, okay, well, there's no reason why we shouldn't be able to have a big list. We just have never thought that that was the main driving factor that we should be focusing on. So we did want to then spend some time there, so we at least put this question out of its misery. And then we need to ensure that there's no missing data across many runs, and we also, this is actually pretty important. We don't want to spend 10 hours collecting mass spectrometry data and then spend 10 days analyzing it. We want it to basically be able to generate results fairly fast. I'm not saying that this means that things need to be super fast, but you get to the point where you don't want that to be the bottleneck. We still expect to be able to look through the data, analyze it manually if we need to, but ultimately the compute time should be relatively reasonable. So the first thing we want to do is remove this spectrum library requirement and say, can we give it protein or peptide sequences and go from there. So if you're going to a new city, you might say, look, I need to I would like to have a cappuccino or espresso, and you could kind of look for these sorts of things in any city. And we wanted basically the equivalent. And this is Sonia Ting took this on as being her PhD thesis project. So the idea is that you have a peptide sequence, you have your DIA data, and could you go and say, look, this signal here is the most likely signal for this peptide. So you would score different things like precursor isotopes, fragment chromatograms, and you'd also then hopefully be able to use this data in a tool like Skyline to be able to provide some sort of quantitative data between different runs. So she came up with a tool we call peptide-centric analysis, and can you just take peptide sequences alone and analyze it from the DIA data. But we are starting with the peptide, not starting from the spectrum. And we take a bunch of peptides, we take a bunch of decoys, and we score them both, and we have a bunch of different scores here. One of I think the biggest innovations was some background subtracting score a contribution that we came up with. And we use a machine learning algorithm that we developed in collaboration with Lucas Schall and Bill Noble in around about 2007 called Percolator to provide not only the machine learning power, but also the statistical inference that gave p-values, q-values, and posterior error probabilities as an output. This was also published in 2017, so the paper's there and provides you with a lot more details. One thing I'll point out is that it became very clear from doing these experiments that again, when you have narrower isolation windows, you gain much better power to be able to detect peptides. And so if you perform gas phase fractionation, so if you had a single injection with 20 mass charge of isolation, you get this purple circle here, and you don't actually identify as many peptides. And if you made 4 injections with 5 mass charge isolation windows, you tended to get a substantially improvement in your ability to detect different peptides and proteins. The reviewers had actually asked us to compare this with DIA Empire. We actually don't think that this is a good comparison, but when you look at wide window data, at least in our hands, I'll point out we're definitely not an expert in using DIA Empire. We got about equal number of things that could be detected by DIA Empire versus PECAN. And when you went to narrower isolation windows from this gas phase isolation, we tended to see a little bit better results than compared to DIA Empire. I think the only reason for this is we also got we get better results on the MS-MS data, while the MS1 data definitely does not improve that much. So DIA Empire looks at correlating product dynes to the MS1 signal, and I think this difference is largely attributed to the ability to be able to find the MS1 signal. And in the PECAN, as you get to narrower isolation windows, automatic gain control improves the product dyne analysis, but does not necessarily improve the MS1 analysis. So this is largely, I think, because we have this improved product dynes, and while PECAN will take in MS1 data as an increased value for its scoring, if it doesn't have it, it still will consider things without it. Brian Searle was trying to speed this up, and one of the things that he came up with was to use like a Sequest or Comet X-score as one of the scoring routines, especially for narrow window isolation data. He has a tool he calls XCORDIA, and it just adds as an extra score. And so we don't have any retention time constraints. We score every single peptide across the entire retention time range. We don't do retention time filtering. We use it as a score in the machine learning algorithms on the back end. And so here you basically get a score across all time, and you can see that this point in time is the most likely time that attributes to the given target peptide. So if you take an entire human FASTA file with 14 or 15 million tryptic peptides, and you take it and you score this against a DIA run going from 400 to 1,000 with 24 mass to charge isolation windows, 12 with their overlapping, which gives you 12 mass to charge effective demultiplex data. And if you compare that to using a fairly standard DDA strategy, we're not doing as well as far as the number of peptides that we can detect. And this is not that surprising, but the overlap between these 3 different runs is much greater than what you'd have with these DDA runs. But in general, we're still underperforming relative to DDA. This does change a lot, though, if you just reduce the contents of the human FASTA to just the proteins that would be present in basically a DDA library. But in general, if we take a very large list of peptides, like 15 million peptides, we have a huge, massive multiple testing problem here. So we don't actually have that much statistical power to basically detect peptides. So this got Brian Searle, who actually is now a postdoc, but was a graduate student in the lab, thinking about ways that he could improve this. And so one of the first things he did is he wanted to take this wide window DIA file. So we incorporated some of the demultiplexing strategies that our lab had used. He also wanted to take our lab's percolator algorithm. He wanted to incorporate some retention time learning in there. He also wanted to make use of the entire spectrum library, not just a set of anywhere from 3 to 8 fragment ions. He wanted to make use of the entire information that was there, and then afterwards do automated transition refinement that could then go into a tool like Skyline for quantitation. So I gave this example 2 days ago, and I'm going to bring it back up to try to illustrate how this tool called EncyclopeDIA works and why we think it has some advantages. So I brought up beforehand, the promise of DIA is that you could take this really, really high resolution image of something like a gigapixel image of like the inauguration, the U.S. inauguration, and you should be able to go in and find anybody's information within there, right? In fact, SciEx has this advertisement, nothing hides from SWATH, right? Well, so can you go and find anybody, can you see a mouse hiding in the back of the audience somewhere? And the answer is obviously no, because that's what the data looks like, right? The data is not of high resolution, it's of poor resolution. So could you really say that any of these people are who you think they are? Probably not at this sort of low resolution. And so the way we kind of solve this is we take some priors. And by priors, I mean, well, we know that basically, the ex-president of the United States sort of sits behind the podium, so we know he should be in this general area. We also know what Barack Obama looks like. We have other photographs from him. So it's sort of like having a spectrum library that was collected on a different instrument, using different collision energy optimizations on a different retention time. We know some information basically about where the president should be, the ex-president should be sitting, and what he looks like. Of course, it looks a little different. Here he's got a red tie on, right? His hair isn't quite as gray as it is here. His eyes are closed here, and here his mouth is open. He's standing behind a podium, and here he's sitting down in a chair. So it's not an ideal match, but it's still better than starting from nothing. We know a little bit about what he looks like, but it's still going to be hard to match him with this image right here. But one big, huge help is we have this retention time constraint. We know this narrow region of where to look, so it gives us a much better chance of finding him than not finding him at all. So when we do this, and we take it, say, a Hela-specific spectrum library that Judith Vienne's lab collected that had about 39 injections, so this was a fair, decent amount of work, but 166,000 peptides are present in it. And if we also took the Panhuman library, which has like 300 injections, this is again an enormous amount of effort to generate this, but 140,000 peptides. We do now get substantially better number of peptides than we would getting by DDA, and also if we just took the DIA data and look for it. There's a couple of things going on here. One is we do have retention time constraints, so we do know approximately where these peptides are, IRT values. We also know information about the intensity of the fragment ions, which is also another great prior. And this gives us a lot of extra power to be able to detect these individual peptides. So this is like doing this, right? So we basically now have a photograph of Barack Obama. We have a general retention time constraints. So Brian started to look into it. He said, okay, if you're using IRT or retention times from other runs applied to a different chromatography setup, you basically get the ability to predict the retention time using a non-parametric approach to about plus or minus 5 minutes. There's not really much else you can do better than that currently. There's some tricks you can get to get slightly better results, but again, we're not doing a retention time, limited retention time extraction. We're taking data out over the entire retention time range. The blue dots are the target peptides, and the red dots are the decoys, and we're using this to assess a false discovery rate of which peptides we believe are real and which ones are not. Okay, and you notice most of the target peptides fall in this sort of plus or minus 5 minute range. So this was the basic idea that he had, which was based off of work that Sonia Ting and Jared Egerton had been doing in our lab, and that is that he wanted to separate the quantitation versus detection. He saw that our lab would have samples come in, and we'd have about 50 to 100 samples come in, and so he said, okay, we can't run 5, 6, 7, 8 injections in every single one of those 100 samples. It would just be prohibitive. We wanted to run 1 injection on those. So those are quantitation samples. Then what we wanted to do is we wanted to take a pool a little bit off of each one of these samples, generate a pool, and then make 6 injections to just calibrate the retention times. So what we're trying to do first is what peptides can we detect in this pool? So these are the peptides present in the sample, and then use that to map information over to the wide window data to perform quantitation. So this data is basically now 4 mass to charge overlapping, so 2 mass to charge effective. We're doing parallel reaction monitoring on everything, right, by making the 6 injections. And then the quant samples, we're basically getting 24 mass charge overlapping, which gives us 12 mass charge effective. It's close to this optimal 10 mass charge that Alexi was talking about yesterday. So this is basically the general idea again. So now what he's done is he's broken up this image. Now, though, at high resolution, so he's actually able to go in at high resolution because we've made this PRM on everything. He's able to say, yes, I found Barack Obama right here, because this is now able to match to that. So you have the spectrum library being matched to the actual chromatographic DIA data. And then what he does, he puts this into what we call a chromatogram library. This now stores the actual intensities of the peaks from the actual DIA data with the collision energies that we're expecting on the DIA column. We actually know the retention time to an extremely well narrow put region in the image, because it's not from a different day, from a different column, from a different event. And we actually store information. We now know he's not standing behind a podium. We know he's sitting next to Joe Biden and in front of Hillary Clinton. And so we know other information about other things he's near in the actual image. So we actually record that information too. We record the information across time. So things like the shape of the peak, et cetera. Oops. The other key thing here is that you can take things and realize that I was not at the inauguration, right? So you don't want to be looking for brain proteins, brain-specific proteins in your Hela lysate or in plasma, right? Because those are just going to create a multiple hypothesis testing problem. So I'm not put into this chromatogram library, okay? So again, so now what we do is now what we're able to do is now we've got this poor resolution data. We've got this high resolution data on column at the inauguration that shows exactly what he looks like in the inauguration. And we know a very narrow region in time, and we have this information going into a machine learning algorithm. We're still looking for everything, and we're not doing a time extracted narrow window. We're just saying that we're going to create a machine learning approach where the retention time now becomes a very big portion of the score. And this is actually showing this right here is now we're able to, that we know that the most peptides are within plus or minus 10 seconds of the best fit line from our chromatogram library. Also, I'll point out too is we show that the improvement of the DDA library versus the wide DIA data is actually, what I showed before showed this on Tuesday, is not a very good measure. Especially when you go to different charge states. But if you actually use the chromatogram library, most of the correct peptides tend to be down on this right-hand side. You tend to get a much better match of the chromatogram library to the wide DIA data. This isn't surprising. We're using the exact same collision energy parameters on the exact same instrument at the exact same time on the exact same column. So it's not surprising at all that we get a much better match of the DIA data from the chromatogram library data versus the wide window DIA data. Okay, so just to kind of give you a little sense of how this works now. So now if I take the FASTA files and I use a tool like PECAN to go and say, in those narrow window DIA data, can I find those FASTA file peptides in it? So I generate basically a chromatogram library in the 6 injection chromatogram library. I can find 53,000 peptides in the 6 injections. And then of those, what fraction can I map over to the wide window data? It's about 47,000. So we're basically now up to the effect of not having to have a Hela-specific spectrum library, or definitely not needing to have a pan-human spectrum library. Of course, this required like hundreds of injections. This required still 30 injections, but this required just 6 injections, right? So we just took 6 injections, took the FASTA file from those 6 injections, found 53,000 peptides, and we're able to show that 47,000 of those were able to map over to the wide window data. If we actually take the information from that spectrum library and say, okay, of all the data that's present in the enormous Hela spectrum library, we can find about 99,000 of those peptides in the actual chromatogram library data, these 6 injections, so the narrow window data, and then about 71,000 of them we can find in our actual runs. Yet, even more impressive, I think, is if you take the pan-human spectrum library, which is collected on a SciEx instrument, you can find about 91,000 of those in our narrow window DIA data injections. And then of those 91,000, about 66,000 can be found in the wide window data. But largely this is because we're correcting the retention time or correcting what the product dye intensities are actually should be on the actual instrument on the DIA data. And I'll also point out, if you take a yeast chromatogram library done, you get nothing. So we're not just getting a bunch of false stuff here. At least we don't believe we're getting a bunch of false stuff here. This is one of the many controls that we've done to kind of assess this. But I'll kind of point out, for the same now amount of instrument time, we're getting more than double the number of peptides that we can detect in a given run. Now I'll point out, I don't really feel like a bigger number is better. I'm happy to stick with this 47,000. I'm actually even happy sticking with this 20,000. But this was largely because people were really worried about what they might possibly be missing. And all it takes is making 6 extra injections from your pool of samples prior to doing your quantitation. Okay, so it's a fairly easy workflow. So this is basically our philosophy, right? So if you can't detect a peptide with a narrow precursor window, you'll never detect it in a wide window data. Don't worry about how big your spectrum library is. Don't worry about anything else. But if you can't find it, don't worry about fractionating. If you can't find it in the narrow window data, you're never going to find it in the wide window data. So just think about it in that regard. Don't worry about all those other aspects of things. The other nice thing about it too is that our DIA data is collected on the same sample matrix, so we're not biochemically fractionating it. So the retention time reproducibility is very high. So on-column retention time calibration overcomes selectivity limitations of poor precursor isolation in DIA. So we know that DIA is a negative component because it's got this poor precursor isolation. You can overcome this by having really, really strong feature in the machine learning for the retention time. It simplifies the workflow. No need to perform extensive fractionation. You don't need to run 33 biochemical fractionations of a reverse phase, strong cation exchange, et cetera. It's just 4 to 6 runs with narrow windows every single time to calibrate your runs. You can take a FASTA file, search against the narrow window data, and then for that narrow window data, you can apply them to the wide window data. But you can make use of large assay libraries. Let's say you are working in a tissue type of which the pan-human library is a representative of that. You could use that to then query the narrow window data. And then use that to map it over to the wide window data. We think that the reason why this large assay libraries help a lot is largely because it's still, even though there's 100,000 peptides are present or in those libraries, there's still substantially less than the 15 million peptides that are in the FASTA file to begin with. So it reduces the multiple testing. It also has a lot of partially tryptic peptides, oxidized methionine, et cetera, that are not present in our just fully tryptic prediction from the FASTA file. So it does have some increased number of peptides that we know are present in the sample, plus also it does not have all the extraneous stuff that we know that we never see. And it really reduces multiple testing. So you only look for peptides you know are in the sample in the wide window data. Don't look for things. This was brought up several times by Isabel and also by Ludovic, by at times having this very large collection of peptides that you're searching for makes that pi 0 number to be too great, and then it makes the multiple testing correction a much bigger problem. So I'll also point out too is that in our lab, we choose transitions using the DIA data, not the spectrum library data. We don't say we're going to use the top 6 or top 7 or top 8 peaks from the spectrum library. We use all the peaks in the spectrum to define whether or not the peak's present. And then for when we use that for quantitation, we actually then look for the median signal across time. In that case, this is the dashed black line. And then we look for, and that tends to be fairly resistant to outliers in the transitions that have interferences. So you see this yellow one, you see the different red ones are excluded then from being considered for quantitation. So we use the ones that are green then for using for our quantitation. And this actually has significant impact. So here today I had shown that if it's library based, you got this improvement in the lower limit of quantitation when you used improved precursor isolation. Yesterday I showed that it didn't matter whether or not you had normal DIA, variable window DIA, or overlap DIA, the quantitation was essentially the same for all different methods. That's because we exclude transitions that have interferences on the DIA data, on the wide window DIA data, and that makes it so we actually are affected much less by artifacts of the actual choosing the actual transitions for quantitation from a spectrum library. This is really easy to do. We hope to have this incorporated in the Skyline as well, and it definitely has been something that we've found has been a fairly powerful approach to improve the quantitation. Tina showed a figure like this. I do want to kind of highlight a couple things about quantitation. One is I really do feel like quantitation is something that people underestimate. People are focused so much on how big their list is that they don't really think about whether or not they can quantify something. And so in order to quantify something, you need to be able to say that the change in signal intensity reflects a change in quantity, whether it's relative quantitation or what people call absolute quantitation. It doesn't matter. You still need to demonstrate you have a linear response. Every time we spend a lot of effort in our lab trying to validate this, and a strategy that we use very commonly is to either for cell lines, we take either 15N or SILAC labeled cells, do, we call it a matched matrix dilution curve of it. For tissues like that are human tissues, we often use the equivalent chicken tissue. We've used chicken livers for human tissue. We've used chicken plasma for human plasma. It's divergent enough and the matrix is similar enough that we can get a accurate reflection of the digestion. Not the digestion, of the dilution. So this is the example of this. So if you take a Saccharomyces cerevisiae, we've calculated the lower limit of quant for every peptide. In here, we've used methods similar to what Olga was talking about yesterday. There's some slight modifications to that, but in general, it's very similar. One key component here is that different peptides for the same gene product obviously have very different lower limits of quantitation. This is being done by diluting BY4741 strain of Saccharomyces cerevisiae with 15N Saccharomyces cerevisiae. We're able to use this to define the limited detection and the limited quantitation. So if you look at all the abundances of the peptide or the proteins from this Gamma Megami 2003 paper, which is shown in this black distribution, there's about 4,000 proteins. If you look at which ones we can detect of those at a 1% Q value, it's about 2,600 of those proteins. If you look at which fraction you can quantify with a precision that's of less than 20%, and an undiluted peptide that's above the lower limit of quantitation, it's more of this blue line. I'll point out that more than half, though, of the peptides disappear, even though the number of proteins don't disappear that much. If you are going to require multiple peptides for quantitation, it drops even more. So it's not, we should stop getting away from we should get away from the number of things that we can detect. We should be focusing on what we can quantify. So do we really care about whether or not we can say that albumin's present in plasma? No, we don't care, because we've known that since whatever, the 1800s, right? So what we care about is whether or not that level of that protein is changing in abundance between different conditions. What's important is the quantity that's changing. And so there's two aspects when you're setting up a quantitative assay that you need to define. It's the limited detection and the limited quantitation. The identification essentially means that you're above the limited detection, but the limited quantitation is a much bigger challenge. And there's generally two figures of merit that people define that. One is the peptide above the lower limit of quantitation using some sort of dilution curve, and the other one is some sort of precision metric on whether or not it has sufficient precision to be able to reflect the changes that you're interested in. So one of the last things I want to kind of mention too is signal calibration. So I have this kind of I think this kind of little, yeah.
So you had, can you go back? So how would you choose, if you have this information, how would you choose peptides to quantify a protein?
We use all of them. Yeah.
Use all of them, even if some of them have
Oh no, you eliminate peptides that aren't quantifiable, right? Yeah.
So different dynamic range. How would you choose?
We would still use all of them. If the undiluted peptide is above the limit of quant, we'd still use them. So if the peptide went below the lower limit of quant in a condition, we would say it's less than this lower limit of quant, but we wouldn't say it is twofold decrease or onefold decrease. It's below or lower limit of quant. Well, I don't know what a protein is, right? So we have the gene, but we know about proteoforms, and we know that the peptides don't always agree with the quantities with one another. So if you take 5 peptides for one protein, they won't agree between different conditions in many cases, and because there's alternative splice forms, PTMs. So I always have a hard time saying we should select these certain number of peptides for a protein. I just want to say that these peptides are well behaved or have some sort of predictive capability. So we have selected certain peptides that reflect the same results as an ELISA before, and that's largely because we know that physicians liked the ELISA response, and not all the peptides gave the same quantitative value as the ELISA, but it's not that we disagreed with the mass spectrometry data, it's just that it didn't give the same correlated results as the ELISA. So we tend to report in our lab almost everything as a peptide level quant. And sometimes we do because reviewers ask us to roll these up into proteins, and there we just take unique peptides. But that's hard too. Alexi brought that up a little bit as well. You could use like a razor strategy, but at the same time, but a lot of it, if you consider like isoforms and things, there's very few peptides, if any peptides, that are actually unique. Okay, so the thing about signal calibration. So people often say they want to do absolute quant. I will argue, and I know that this is an extreme opinion, that there is no such thing as absolute quant. Absolute quant is just relative quant relative to something that someone's defined as a reference material. And I also challenge you, order a peptide from a vendor that had amino acid analysis. Take that peptide, aliquot it into 5 different things, identical amounts, send it back to that vendor and say, give me amino acid analysis on it. We've done this now. Our colleague Andy Hoofnagel's done it. And you'll see that they say that their assay has within plus or minus 5% CV, and at times you'll see 50 to 100% CV between those 5 different samples of the exact same amount. So I think there's almost no way that you can trust the quantity coming back from the amino acid analysis from those vendors. So I really don't believe that you can really do that there's such thing as absolute quant. It's just measuring something relative to something that you've called and defined. And this is basically everything that's in quant, right? So scale is arbitrary, but placing things on the same scale is important. So if you have data from a QE or a triple TOF, you want to be able to compare the results to one another, right? So you want those data to be on the same scale. It doesn't matter what the scaling is, you just need to make sure that you get the same results from the triple TOF and the QE. And the scale is often arbitrary. So kilogram, right? So what is it? It's like, well, there's literally a kilogram in Paris that someone says, this is the kilogram, and everybody else has made their measurements of kilogram relative to that one in Paris, right? NIST in the United States, National Institute of Standards and Technology, has made a replica of it. But again, it's a relative measurement relative to that Paris kilogram. And it was originally defined as being a mass of a liter of water freezing point, but now it literally is the kilogram that's in Paris, France, okay? That's what a kilogram is. A meter is, again, there's a value, there's a standard one. There is physically actually a meter stick that is used that all other meter sticks are defined from. It was originally about 1/10,000,000th of distance from the equator to the North Pole was how it came about. I came from an isotope ratio mass spectrometry background, and when you measure 13C isotopes, you always report things relative to this fossil called PD belemite. It was a fossil found in this formation, this rock formation in South Carolina in the United States, and it's completely arbitrary. It's just they measured everything relative to that. Guess what? No one's been able to find this fossil again. So now what people have is people have references relative to PDB, and they make their measurements relative to the reference, which was measured relative to reference to the PDB. It's completely arbitrary what the scaling is. It doesn't matter as long as everybody makes their measurements relative to the same reference material. 18O isotopes are measured always relative to this thing called standard mean ocean water. This was this guy, Harold Craig at the Scripps Oceanographic Institute, went around the Earth, and from all oceans and major seas, he actually collected a bucket, and he filled it with water from those different oceans. And then he said, this is what this is standard mean ocean water. Everybody's going to measure the 18O measurements relative to this. And then, of course, that bucket ran out. And then people made other measurements where they made their buckets relative to the standard mean ocean water. And then they made other working measurements. But everybody still reports it relative to that original bucket that doesn't exist anymore. So basically what you want is you have a series of quantities measured maybe on 2 different instrument platforms in 2 different labs. One instrument may be responding better than another one. It's uncalibrated signal to basically be put on the same scale. And so how do we do this? So Lindsay Pino in her lab has been thinking about this a lot. This has basically been her PhD thesis, is how do we go about doing this? So it's all about using a common reference material. So here's a common reference material. You define the quantity. You can call it 1 if you want to. I don't care. You can call it, or you can set that value as being the value that came back from ELISA. It could be some value that's known a quantity in that sample. Different labs may have working standards, working references relative to that value. So some may be, it's just like an IRT value. It's no different than an IRT. You're just calling it a arbitrary independent retention time. And then if people then measure their working references relative to that IRT standard or the IRT quantity, then you have these experimental samples where you measure the quantity relative to those as well. This then puts everything in the same scale. The big question is, what should we use as a reference material? And I won't dictate that for you. I can say that every project we start in the lab right now, every collaboration we start in the lab, I get all of our collaborators to think about thinking 10 years down the road. Let's make sure we have a reference for which we can be making the measurements for in another 10 years. There will be different instrument platforms, different hardware, different experiments, but I'm sure what you're going to want to do, the 100 samples we're doing now are not going to be the 100 samples you're only ever going to be interested in. There's going to be another 100 or 1,000 over the next 10 year samples that you're going to measure. So what are we going to make all those measurements relative to? And it doesn't even matter if that reference material runs out. We just have to make a new reference material before it runs out to calibrate that working value relative to it. So I want to give one example. This is Lindsay was doing a lot of work using osmotic shock in the lab of yeast, and she was excited when this Selectivity paper came out in 2015. She knew also what was cool about it is that paper did almost identical osmotic shock conditions as what she had in the paper. They also had as one of their measurements this BY4741. Standard, which was grown under almost identical conditions as what she had as well. So what she did first is she took her osmotic shock sample and her reference, this BY4741. She prepped it on 2 separate days, and she measured them on 2 separate days on the same instrument. She showed, basically there's good uncalibrated areas basically give fairly good correlation. When you calibrate them, it doesn't improve it that much. That's not surprising because they're prepped by the same person. They're on adjacent days on the same instrument. It's not that big of a deal. She was also making measurements on our triple quad and Altus and relative to her DIA data. And she knows, of course, the signal intensities aren't calibrated relative to one another, so the uncalibrated areas don't correlate that well. When she measures all of the values on one of the samples, the osmotic shock samples relative to her reference, and she measures her on both the SRM and the DIA, she gets much better correlation. So this becomes much better calibrated. If you look at the Selectivity paper, you'll notice that in that paper, it's really great, that paper, and in there they actually do mention, they said, the signal intensities on the Q-trap and the triple TOF are not comparable, so they're uncalibrated, we can't compare the intensities, but they're only measuring the relative intensities. And that's true. If you actually take the raw SRM data from there and the SWATH data, they are fairly well correlated, but they're not very well calibrated to one another. If you calibrate their data relative to their reference and their SWATH data relative to the reference, they actually get really good calibration and they fall directly on this line of unity. And if we take even more great was when Lindsay took the Selectivity SWATH data, her DIA data on a Q-Exactive. Obviously the intensities were not correlated at all, and they were not even slightly related. But when she calibrated the SWATH data relative to their reference and her data relative to her reference, they end up becoming definitely very well correlated. The same thing's true actually when she took her DIA data and relative to the Selectivity SciEx Q-trap data. So what this basically means is that if this is a worst case scenario, They're using a different reference sample than we are. We're assuming that because it's the same strain grown under the same conditions, they'll have the same amount of protein expression. But of course, there's definitely going to be different mutations that are accumulated in different strains. There's also going to be slightly different preparations of media. This is an absolute worst case scenario, but we've demonstrated, at least she's demonstrated, that they can get fairly good calibration of signals between labs and definitely between instrument platforms. So the last thing I would do, I know I'm getting close up to the end of the line, is talk a little bit about some of the challenges I think about with DIA, and this is going to get brought up by other people as well. But positional isomers is one thing that we've definitely seen as a major struggle. So if you have these two different phosphorylation sites, both of them have very different functions. They have exactly the same mass. They have exactly the same elemental composition, and few fragment ion masses may differ. At retention times may differ. They may not differ. So look at these peptides. There's two different peaks in the product ions for these phosphopeptides. And if you look at the localizing fragment ions, so the fragment ions that fall between the different, that can localize specifically the modifications to one phosphosite versus the other, you can see that there is actually the ability to distinguish between which form is which. I'm not sure if people remember, there's this paper from Gavin Reed that talks about gas phase rearrangement. We're definitely seeing some examples of that right here. In fact, here is this peptide rearranging to the other site, to this site from this site. And this peak right here is the opposite thing happening. So this phosphorylation site rearranging to here. But still, we have some sort of retention time separation that allows us to distinguish between them. There are cases where we don't actually have the ability to distinguish between them. Here's the precursor chromatogram. They're unresolved. Here are the partially resolved product ion chromatograms. You look at the localizing fragment ions here, you can see that, that there is the ability to distinguish between the different two forms. I won't go into details, but there's an algorithm. There's a tool called Thesaurus. It's submitted. It's actually, the software is available. It's on Bitbucket. And it allows you to basically take output from this tool EncyclopeDIA and localize the different fragment ions and calculate probability scores of which location. So one thing that the VN lab had noticed at one point in time is that most phospholipeptides in human cell lines exist in multiple localization states. So greater than 50% of every phospholipeptide will have another phospholipeptide present at a different site. Regardless of whether your DDA data showed that or not, 50% of them do. And so this is actually a really important problem, and it begins to bear question of whether or not phosphoproteomics can even be done on the DDA level, right? Because in that case, you trigger on the first phosphopeptide that you see, and dynamic exclusion will prevent you from triggering on the second one. If you run the same sample enough times or under different fractions, you tend to sample some of these other forms, but in general, they tend to go a little bit missed. The other thing that's a little bit scary too is that many positional isomers elute within 60 seconds of each other. So if you look here, most of the number of the peptides between two different positional isomers are within 1 minute of time. An enormous quantity of them are within a few seconds of one another. When you do this by DDA, of course, we don't even have the ability to detect ones and differentiate those between DDA and using an algorithm like the GigaLab A-score to distinguish between the different positional isomers. So I want to give a couple examples. There's two different examples I'm going to give. This is this iris signaling pathway. There's three major phosphorylation sites that are important, and they all have slightly different regulative aspects. So there's this tyrosine site, which so insulin binds the insulin receptor, phosphorylates this phosphotyrosine. These are all on the same phospholipeptide. The VN lab spectral library had these two forms in it. And you can also give there's this feedback loop through AKT, and there's drugs that are used to inhibit this AKT phosphorylation of mTOR. And so the spectral library is used to assign these two different peaks to these different positional isomers. And then Thesaurus looks up and downstream over a certain range to find any other positional isomers, and it finds a phosphotyrosine site over here. We've done this with insulin stimulation, IGF-1 stimulation, and also with an AKT inhibitor. And the interesting thing here is that this one specific site that's regulated by this AKT, when you add the AKT inhibitor, we do see a decrease, and all the other ones we don't see an effect and difference between the DMSO and the AKT inhibitor. Here's another case where they're not resolved chromatographically at all. So here's this one phosphorylated site, and there's actually a difference in intensity between with the AKT inhibitor and without. And we see a decrease in site. This other site, we see no difference in intensity. These are not chromatographically resolved at all. They're at the exact same retention time, and the only way that you'd be able to analyze this data is using positional sequence-specific fragment ions. I do want to bring up one last thing. I think I'm over by about 9 minutes right now. It'll be, bear with me for like 3 more minutes. But this is, I think, a challenge in analyzing peptide-centric data. This is an advantage, actually, of taking an approach like DIA umpire. But if you use 2 master charge wide isolation windows and you look for its oxidized methionine, you would see this individual peptide or peak right here at this 21 minutes. If you take the oxidized one with a 2 master charge isolation window, you would see this predominant signal at 27 minutes. If you use a 24 master charge precursor isolation window and you look for the oxidized methionine, you see a little signal at 20, but it's actually because almost all the fragment ions are shared with that of the oxidized, the non-oxidized window, and this one is about a factor of 10 more intense. This one scores much higher at this retention time. For the oxidized peptide sequence, notice it's at the N terminus, so almost all the Y ions are shared. And so what you do is you falsely, incorrectly assign this individual retention time, the unoxidized signal, to that of the oxidized peptide. And so we've come up with a variant-specific scoring. And if you look across things over a wide retention time, you notice that here's the correct data with the 2 mass charge wide isolation window. If you look across a wide retention time window, a third of the oxidized peptides are incorrectly detected at the retention time corresponding to the more abundant unmodified form. This also occurs with sequence variants and homologous peptides. So these are 2 sequences in a FASTA file. They have exactly the same elemental composition. And if you look at a score relative to a spectrum library, they're indistinguishable from one another, or basically indistinguishable from one another. You'd say that both of them are present because beyond some random chance. But when you actually only look and say, look, I'm required to have sequence-specific ions distinguishing between these 2 different forms, there's only one that's actually present. So if this one was the only one that was in your sequence database or a spectrum library, and this one is not, you would never know that you're incorrectly assigning this to this sequence. And we're not quite sure yet how to resolve this. So in conclusion, we do have the ability to perform DIA with selectivity of 50% the precursor isolation window across the entire mass range. We can also do MSX to improve it even bit more. I believe we're getting dynamic range and sensitivity that approximates PRM, but is comprehensive across the mass range. We have tools that can handle peptide detection without using libraries in a peptide-centric way. Gas phase fractionation to build on column DIA libraries is definitely a very simple workflow. It improves the overall ability to detect peptides and analyze them, and it doesn't rely on whether or not the libraries are collected on the same type of instrument or platform, et cetera. You can make use of other libraries from other labs and other groups. We focus on quantitative figures of merit instead of the binary presence and absence. So quantitation really should be this key focus for people. And we definitely need to be putting all of our assays on the same quantitative scale so that our quantitative data are commutable between labs, platforms, et cetera. And of course, I want to thank the group in the lab, and thank you very much for your attention. I'm happy to answer any questions. Yes.
When you're adding in standards and putting in a reference sample, how do you add the standard in? Do you then measure pipette error, and how much do you calibrate your pipettes?
Yeah, so it's an external calibrator. So when you do your BCA assay, you've got an external calibrant using albumin or IgG, right? It's the same thing here. You have one of your samples, and it's a single point external calibrant. You treat it exactly the way you use your albumin calibrant in your BCA assay. You're measuring all your measurements relative to that, and that's it. And we know actually that albumin's a very poor calibrator for a BCA assay. There's no way that albumin is reflective of the quantity of a Hela cell lysate. There's just no way. But people still calibrate relative to albumin because everybody can calibrate relative to albumin, right? So it's an easy thing to do. It's not saying that there's that many micrograms of protein. It's saying I have this many, assuming 1 microgram of albumin. So that's why I don't really believe in absolute quant. It's just what are you make your measurements relative to. So yeah, and the other key component here is that LabCorp in the United States, it's a clinical chemistry lab, they have this fantastic paper out right now that shows that basically peptide calibration, the stable isotope label isotope dilution just doesn't work for peptides, for proteomics. And the main reason is that one, the AAA isn't a good measure of what the peptide presence is, and two is that digestion isn't really accounted for. So using the single point external calibrant actually is a more precise measure because it gets prepped every single day. So if your digestion goes to 50% on one day, it goes to 50% in your external single point calibrator. So it's a much better correction for batch to batch, day to day variance. And Andy Hoofnagel, who's a clinical chemist at the University of Washington, has great data showing that too. It's actually more precise to use an external calibrant than it is to use an internal calibrant. Now, it helps if you have the internal calibrant. It doesn't hurt if you have it in there. It just corrects for some ionization differences and stability of peptides. But in general, if you have stable peptides and everything else, and your measurements are precise, then the calibration to an external single point calibrator tends to be better.
I would have one question actually.
This one works.
Okay. So I was wondering, so this might take a second.
Yeah.
So you have the small window data, you have the big window data, and the small window data you're querying with the FASTA. So you're sort of have lots more queries without the prior information, but you make up for that by having better quality data, right, with the small precursor isolation windows. And so it occurred to me that so now let's go to ASMS, where we saw like a lot of talks about spectrum prediction and retention time prediction. And it seems like based on these large synthetic peptide libraries, this is maybe the first time where it looks like it starts to work properly. And people are saying, oh, we could use these very large scale predicted spectrum libraries for querying DIA data, which I think directly is not really, we know reasons now why that might not be a good idea, but it seems like in your workflow, it might be a good idea because you'd be replacing a FASTA file that doesn't have much prior information with basically the same set of peptides, but now you've generated some priors for that. So have you thought about that?
Yeah, so I really think about one way to do is to kind of wipe your mind at this idea of spectrum libraries in my mind. So it's just priors. Do you have other pieces of information that you're using to be able to help you assign the correct retention time? And so, yeah, so in our case, we found if we have no priors, so only the peptide sequence, we know the B and Y ion fragment masses that should be there, but we know nothing about the retention time other than SSR calc, hydrophobicity. And that is one of the PECAN scoring routines in there. But we don't do very well. But now if you took into that some information about the fragment ion intensities, you'd probably get somewhere between this intensity and the spectrum library, right, by itself. If you have narrow window data, you're probably going to do better than what's here because this is assuming just the FASTA file across with 14 million peptide sequences being scored against the narrow window data, and that narrow window data then being scored against the wide window data. So it'd probably be doing somewhere better than this, but not quite as well as if you actually had a chromatogram library based on the Hela specific library. That's because this advantage and gain over this is largely because it's not querying against the 14 million peptides in the FASTA file. Plus, it's looking for oxidized methionine and other things, or a partially tryptic peptide, or certain miscleavage events that we know were present in the spectrum library, but may not have been considered when we just took the FASTA file by itself.
So if you did this, I mean, the predicted way has the benefit of you still being able to query for whatever you want and not relying on empirical observations in the library. So if these predictions actually worked, it seems like it would be a good replacement for your FASTA input.
So I think it would be something like between here,
okay,
without having to do much else. So
all right, anything else? If not, let's go to coffee and try to come back at 11:10 for the tutorial. Thanks.